Welcome to DAR Tutors for online and home tuition. In this video, we will explore the fundamentals of bivariate statistics, a key topic in the IB Mathematics Analysis and Approaches higher-level curriculum. By the end of this session, you will be able to understand and describe the association between two numerical variables, calculate and interpret Pearson's product moment correlation coefficient, and draw and use a line of best fit for prediction. Let's begin by defining what we're working with. Bivariate data consists of two variables for each individual or item in a sample. Our goal is to analyze the relationship between these two variables. When we analyze bivariate data, we often identify one variable as the independent or explanatory variable, and the other as the dependent or response variable. The independent variable is the one we believe might influence the other, and it's typically plotted on the horizontal axis. The dependent variable is the one we are trying to predict or explain, and it's plotted on the vertical axis. For example, if we study the relationship between the number of hours a student studies and their test score, the hours studied would be the independent variable, and the test score would be the dependent variable. The most effective way to visualize the relationship between two numerical variables is by using a scatter diagram. A scatter diagram is a graph where each point represents a pair of data values. The independent variable is on the x-axis, and the dependent variable is on the y-axis. Let's consider an example. Imagine we have data on the age of athletes and the distance they can throw a discus. Here is a table of data. We'll plot age on the x-axis and distance on the y-axis. As we plot each point, we can start to see a pattern emerge. For instance, the point, 10, 15, represents an athlete who is 10 years old and threw the discus 15 meters. By looking at the overall shape of the points, we can describe the correlation or the relationship between the variables. We consider several characteristics. First, the direction. If the points generally go up from left to right, we have a positive correlation. If they go down, it's a negative correlation. If there's no clear trend, there's no correlation. In our discus example, as age increases, the distance thrown also tends to increase. This is a positive correlation. Second, linearity. If the points cluster around a straight line, the relationship is linear. If they follow a curve, it's nonlinear. Our discus data appears to be roughly linear. Third, strength. This describes how closely the points follow the trend. We can describe it as strong, moderate, or weak. The discus data points are fairly close to the line, suggesting a strong positive correlation. Fourth, outliers. These are points that lie far away from the general trend of the data. Our discus data doesn't have any obvious outliers. Finally, causation. It's crucial to remember that correlation does not imply causation. Just because two variables are related doesn't mean one causes the other. For example, the number of ice cream sales and the number of drownings are positively correlated, but ice cream doesn't cause drowning. A third variable, temperature, causes both. So, to recap, we can describe the relationship between two variables by looking at a scatter diagram and considering its direction, linearity, strength, outliers, and the absence of causation. While describing correlation by eye is useful, it's subjective. To get a precise, objective measure of the strength and direction of a linear relationship, we use Pearson's product moment correlation coefficient, denoted by R. This coefficient, R, is a single number that quantifies the linear correlation between two variables. The formula for R is complex, and you are not required to memorize it for the IB exam. However, you must be able to calculate it using your graphics calculator. The formula involves the sum of the products of the deviations from the mean for both x and y, divided by the product of the standard deviations. This calculation is best left to technology. What you do need to know are the properties of R and how to interpret its value. First, the value of R always falls between a 1 and +1, inclusive. Second, the sign of R tells us the direction of the correlation. A positive R means a positive correlation, and a negative R means a negative correlation. If R is exactly 0, there is no linear correlation. Third, the size or magnitude of R tells us the strength of the correlation. A value close to +1 or 1 indicates a very strong linear relationship. A value close to 0 indicates a very weak linear relationship. To help us interpret the strength, we can use a guide. This table provides a general framework. For example, an R value between 0.87 and 0.95 is considered a strong positive correlation. Remember, these are guidelines, and the context of the data is always important. Let's work through an example to see how to calculate and interpret R using a calculator. A botanical garden tests a new chemical to control beetles. They record the quantity of chemical used and the number of surviving beetles. First, we enter the data into our calculator's list editor. Let's put the quantity of chemical in list 1 and the number of beetles in list 2. On a TI-84, you would press Stat, then Edit, and enter the values. On a Casio, you'd go to the Statistics menu. Make sure your calculator is set to calculate linear regression. Next, we perform the linear regression calculation. On a TI-84, you'd go back to Stat, then KLT, and select Lin Reg Shisasi Axasisi. On a Casio, you'd go to KLS, then REG, and select Lin Reg. The calculator will output several values, including A, B, R squared, and R. In this case, we find that R is approximately 0.859. Now, let's interpret this value. The sign is negative, so we have a negative correlation. The magnitude 0.859 falls into the strong category according to our guide. Therefore, we can conclude there is a strong negative correlation between the quantity of chemical used and the number of surviving beetles. This means that as the quantity of chemical increases, the number of surviving beetles tends to decrease. If we find a sufficiently strong linear correlation, we can model the relationship with a line of best fit. This line allows us to make predictions. A line of best fit is a straight line that best represents the linear trend of the data on a scatter diagram. There are two main ways to find this line: by eye or using the least squares method. For the IB exam, you need to be able to do both. Drawing a line of best fit by eye is a visual estimation. The goal is to draw a line that follows the trend of the data, with roughly the same number of points above and below it. A helpful technique for drawing a line of best fit by eye is to first calculate the mean point of the data. The mean point has coordinates, x bar, y bar, where x bar is the mean of all the x values and y bar is the mean of all the y values. This point will always lie on the line of best fit. Let's use the discus throw data again. The mean age, x bar, is 15 years, and the mean distance, y bar, is 29 meters. So, we plot the mean point, 1529, on our scatter diagram. Then we draw a straight line through this point that seems to fit the overall trend of the data. The second, more precise method is the least squares regression line. This is the line that minimizes the sum of the squared vertical distances from each data point to the line. It's the most accurate linear model for the data. The equation of this line is typically written as y hat equals ax plus b. Here, y hat represents the predicted value of the dependent variable. A is the gradient, and b is the y-intercept. Your calculator will give you these values when you perform a linear regression. For the discus data, the least squares regression line is y hat equals 2.8x minus 13. This means the gradient is 2.8 and the y-intercept is 13. This line is the most accurate linear model for this data. So we've learned how to find a line of best fit, both by eye and using the least squares method. This line is our tool for making predictions. Now that we have a line of best fit, we can use it to make predictions. There are two types of predictions: interpolation and extrapolation. Interpolation is making a prediction for an x value that is within the range of our original data. Extrapolation is making a prediction for an x value that is outside the range of our original data. Let's use our discus throw data and the regression line y hat equals 2.8x minus 13. The ages in our original data range from 10 to 20 years. This is our data range, or the poles. First, let's try an interpolation. We'll predict the distance a 14-year-old athlete might throw. Since 14 is between 10 and 20, this is an interpolation. We substitute x equals 14 into our regression equation. This gives us a predicted distance of 26.2 meters. Now, let's try an extrapolation. We'll predict the distance a 50-year-old athlete might throw. Since 50 is outside our data range of 10 to 20, this is an extrapolation. Substituting x equals 50 gives us a predicted distance of 127 meters. It's crucial to comment on the reliability of these predictions. Interpolations are generally considered reliable, provided the correlation is strong and linear. Our prediction for the 14-year-old is reliable because it's an interpolation within a strong linear trend. Extrapolations, however, are often unreliable. They assume that the linear trend we observed in our data continues indefinitely, which is rarely true in the real world. Our prediction for the 50-year-old is unreliable. A 50-year-old throwing 127 meters is far beyond the current world record. The linear model is likely not valid for ages outside our data range. So, when making predictions, always state whether it's an interpolation or extrapolation and comment on its reliability based on the data and the context of the problem. Let's solidify our understanding with a more complex example, similar to what you might find in an IB exam. A researcher investigates the relationship between the number of hours students study for a test and their final mark. Here is the data. First, let's draw a scatter diagram to visualize the data. As we plot the points, we can see a general upward trend. However, notice the point at 4.558. It's significantly higher than the other points with similar study hours. This is an outlier. Outliers can heavily influence our calculations. The problem asks how it should be treated. If an outlier is a genuine piece of data, it should be kept. If it's a recording error, it should be discarded. In an exam, you would state this principle. For our analysis, let's assume it's a genuine but unusual result and keep it for now. Next, let's calculate the correlation coefficient R using our calculator. After entering the data and performing linear regression, we find that RR is approximately 0.73. This indicates a moderate positive correlation. As study hours increase, test marks tend to increase. Now, let's consider the question of causation. Does studying more hours cause higher marks? While there's a strong correlation, we cannot definitively say it's causal. Other factors, like a student's natural ability, prior knowledge, or the quality of their study, could also influence the mark. Correlation does not imply causation. This example demonstrates how to handle outliers, calculate R, and discuss causation, all essential skills for the IB exam. Let's work through one more example, focusing on the least squares regression line and its use in prediction. A company records the number of workers on a job and the time it takes to complete it. Here is the data. First, let's calculate the correlation coefficient R to see if a linear model is appropriate. Using our calculator, we find that R is approximately 0.93. This is a very strong negative correlation. As the number of workers increases, the time to complete the job decreases. Since the correlation is very strong and linear, we can find the least squares regression line. The calculator gives us the equation y hat equals 1.2x plus 10. This is our model for the relationship. Now let's use this line to make a prediction. We'll predict the time it would take to complete a job with 4 workers. The number of workers in our data ranges from 1 to 8. Since 4 is within this range, this is an interpolation. We substitute x equals 4 into our equation, giving us a predicted time of 5.2 hours. Let's also predict the time for a job with 10 workers. Since 10 is outside our data range, this is an extrapolation. Substituting x equals 10 gives us a predicted time of 2 hours. This is clearly impossible. This example perfectly illustrates the danger of extrapolation. The linear model is a good fit for the data we have, but it breaks down when we try to apply it to situations far outside that data. The prediction for 4 workers is reliable because it's an interpolation. The prediction for 10 workers is unreliable because it's an extrapolation that yields an absurd result. To conclude, let's recap the key concepts we've covered today. We started by defining bivariate data and visualizing it with scatter diagrams. We learned to describe correlation by its direction, linearity, and strength. We then introduced Pearson's correlation coefficient, R, as a precise measure of linear correlation and learned how to interpret its value. Finally, we saw how to find and use a line of best fit to make predictions, distinguishing between reliable interpolations and unreliable extrapolations. Mastering these concepts is essential for success in the IB Mathematics AAHL course. Now let's test your understanding with some practice questions. Here are 5 practice questions designed to reflect the style of the IB exam. Take your time to work through them. Question 1 asks you to describe the correlation from a scatter diagram. Question 2 requires you to calculate R and the regression line from a table of data. Question 3 involves an outlier. Question 4 asks for a prediction. And question 5 tests your understanding of causation. Pause the video now and attempt these questions. The solutions will follow. Welcome back. Let's go through the solutions to the practice questions. For question 1, the scatter diagram shows points that are quite spread out but still follow a general downward trend. Therefore, we can describe this as a weak negative correlation. For question 2, we enter the data into our calculator. The linear regression function gives us R is approximately 0.96, which is a very strong positive correlation. The equation of the regression line is y hat equals 1.5x plus 2. For question 3, the outlier is the point 야산시친 2. It lies far below the general trend. With the outlier, R is about 0.78. Without it, R jumps to about 0.98. This shows how much an outlier can weaken the correlation. For question 4, we use the regression line y hat equals 1.5x plus 2. To predict y when x is 6, we substitute x equals 6, getting y hat equals in. This is an extrapolation, as 6 is outside our data range of 1 to 5, so the prediction is unreliable. For question 5, the strong positive correlation between ice cream sales and drowning deaths is not causal. The underlying cause for both is a third variable, temperature. As temperature rises, more people buy ice cream and more people go swimming, increasing the risk of drowning. Well done if you got these correct. If not, review the relevant sections of the video. Thank you for watching this Dart Tutors video on bivariate statistics.